Okay, let's unpack this. Often, when we think about a scientific field, our minds go straight to the equations, the concepts, the dry facts. But today, we're doing a different kind of deep dive. We're going behind the textbook and the lab bench to meet the brilliant, sometimes eccentric, and often dramatic minds who actually built the very foundations of organic chemistry. Our map for this journey: a truly illuminating collection of insights from Chapter 21, 10 or so, Great Organic Chemists from Organic Chemistry I for Dummies, seconded.
And what's fascinating here is how these individuals, spanning centuries and vastly different approaches, collectively shaped a field that touches almost every part of our lives. Our mission today is to extract not just what these pioneers discovered, but how their contributions transformed chemistry, revealing surprising human stories in the broader context of their times. We'll see how organic chemistry, in its essence, is a testament to human ingenuity, from philosophical groundwork right up to engineering complex molecules, and even developing new computational tools.
And trust me, by the end of this deep dive, you'll have a new appreciation for the science and definitely some unexpected stories that will stick with you. Making this potentially dense topic incredibly engaging and memorable, I'm genuinely curious to see how their personal quirks and struggles influence their monumental work. So, let's dive into the pioneering spirits of organic chemistry. We're kicking off with a really radical shift in scientific thought, one that completely overturned a long-held belief. We're talking about the overthrow of vitalism, spearheaded by Friedrich Wöhler, who lived from 1800 to 1882.
Right. For centuries, people believed that organic molecules, basically anything that came from living things, contained some sort of special vital life force. It meant you could never create organic compounds from non-living inorganic materials. It was almost a philosophical barrier in chemistry. Wöhler absolutely shattered this idea in 1828. He took inorganic ammonium cyanate and, well, through a remarkably simple reaction, synthesized urea.
Urea, which is a very organic molecule found in urine. So he essentially created life from non-life, or at least a key component of it. That's quite a mic drop moment.
Precisely. It wasn't just a clever lab trick. It was a profound blow to vitalism. It proved that organic chemistry wasn't some mystical art, but a systematic science where compounds could be understood and manipulated. It really paved the way for the entire field we know today. It was like finally realizing you could build a house with bricks you made yourself instead of only using bricks found in nature.
That's a great analogy. So from redefining what organic matter is, we move to how we visualize it. This brings us to August Kekulé from 1829 to 1866. Now, the source hints he wasn't exactly a charismatic lecturer, but his ideas, revolutionary and crucially correct.
Absolutely. Kekulé's most significant contribution was correctly positing that carbon atoms could form four bonds, and more importantly, that carbon atoms could link together to form long chains and closed rings. This sounds obvious to us now, right? But at the time, it was a massive conceptual leap. It allowed chemists to finally understand the incredible diversity and complexity of organic molecules.
I remember the story about his breakthrough with the benzene ring. It's pretty legendary, this idea of a snake biting its tail. Is that just a charming anecdote, or, do we believe it?
Well, Kekulé himself famously claimed the inspiration struck him in a dream of an Ouroboros, a snake eating its own tail, which suggested the cyclic structure of benzene. Whether it's entirely true or, a good story for the scientific record, it's certainly memorable. It captures the intuitive leap required to visualize something so abstract back then. What's truly important is that his idea of a hexagonal ring for benzene, C6H6, was accurate and unlocked a huge area of chemistry.
Kekulé's story of the benzene ring is legendary, yeah, whether the dream was real or not. But it raises a really interesting point about how scientific discoveries are made and, crucially, who gets the credit. Because our next pioneer, Archibald Scott Couper, who lived from 1831 to 1892, has a truly fascinating and tragically sad story. But it's a very human spin on the race for scientific priority.
Couper's contribution was immense. He actually proposed the tetravalency of carbon, meaning carbon forms four bonds before Kekulé. But here's where the drama unfolds. His PhD advisor, a man named Wirtz, actually held back Couper's paper from publication. Why? Because Couper's paper was quite forceful, apparently, in rejecting the current entrenched theories of the time. This delay meant Kekulé published his own paper first, effectively scooping Couper.
So he was literally sabotaged by his own advisor, lost the recognition he deserved. That's just heartbreaking. A true academic tragedy.
It really is. As you can imagine, Couper was outraged. He angrily confronted Wirtz, who then promptly dismissed him from his lab. The source indicates that after this traumatic event, Couper suffered a nervous breakdown, became mentally ill, and spent the remainder of his life tragically confined to his mother's attic. His story isn't just a sad anecdote, it's a stark reminder that even in the pursuit of truth, ambition and academic gatekeeping can brutally reshape lives, and even alter the recognized history of discovery. It underscores the immense pressure and sometimes cutthroat nature of science even today.
That's a profound lesson, the human cost of scientific progress. And if we're talking about forgotten pioneers, we have to shine a light on Johan Josef Loschmidt, 1821 to 1895.
Loschmidt is indeed one of those often overlooked figures. In 1861, he published a pamphlet called Chemische Studien. What makes this truly remarkable is that it contained two-dimensional structural representations of hundreds of organic molecules. Think about that. At a time when the very idea of a molecular structure, beyond just a simple formula, was still novel. He was drawing out these detailed representations. It's like he was sketching blueprints for molecules before most people even agreed molecules had a consistent architecture. And astonishingly, many of his structural guesses turned out to be accurate. Some even credit him with predating Kekulé in depicting a cyclical representation for benzene, using a circle to denote it. Makes you wonder how many other unsung heroes are out there in scientific history. From the flat, two-dimensional blueprints, we now shift our focus to the crucial three-dimensional nature of molecules. This introduces us to Louis Pasteur from 1822 to 1895 and the mind-bending concept of handedness in molecules. Pasteur's discovery was a pivotal moment for understanding stereochemistry, the study of how molecules are arranged in three-dimensional space. He observed that tartaric acid formed two distinct types of crystals. And here's where it gets really interesting. He literally separated these two types of crystals by hand, using tweezers under a microscope. It sounds painstaking, but what he found was incredible. He noticed that when plain polarized light passed through one type of crystal, it rotated in one direction, and through the other type, it rotated in the opposite direction.
So like a left-handed glove versus a right-handed glove. And he figured this out just by picking them apart. That's incredible. What was it about his method or his mindset that allowed him to see something others missed for so long?
Exactly. He intuitively grasped that this difference in light rotation and crystal shape must relate to different spatial orientations of the atoms within the molecules. Basically, that molecules could be mirror images of each other, like your left and right hands. He was absolutely right. And this laid the foundation for our entire understanding of stereochemistry. This matters immensely for you because in the real world, particularly in drug efficacy, often only one-handed version of a molecule will work in our bodies, or even be safe. Think of it like a key fitting a lock. Only the correct handed key will work. It's crucial for biological processes as many biomolecules themselves are handed.
That's a concept I hadn't fully grasped, and the real-world implications are huge. It makes me wonder how long it took for others to really catch up. That must have been a massive leap, moving from 2D to 3D. And speaking of complexity, next we have Emil Fischer, 1852 to 1919, a true early genius, despite his own father doubting his business acumen.
You hit on a key point there. Moving from 2D to 3D understanding was a huge leap, and our next chemist, Emil Fischer, truly mastered that, especially in the world of sugars, which are incredibly complex in their spatial arrangements. Fischer defied his father's expectations, went to the University of Bonn to study science, and became a true pioneer. He dedicated significant work to synthesizing and determining the structures of sugars. He even discovered their DL stereochemistry, essentially, how these sugar molecules twist in space. A critical detail because, just like our hands, one version might fit a biological glove while the other doesn't, impacting how our bodies use them for energy.
So he figured out the precise 3D blueprint for these essential energy molecules. That's amazing.
Exactly. And it didn't stop there. He made major advances in understanding nucleotides. Think of them as fundamental building blocks, like specific letters in the chemical alphabet that form the very ladder of our DNA. Compounds like adenine and guanine. Unraveling their structure was like cracking a piece of the genetic code itself. Sadly, though, while his career was marked by incredible creativity, his life ended tragically. He suffered from the side effects of toxic mercury compounds he worked with in the lab. And after his wife died and two of his three sons were killed in World War I, he took his own life. It's a somber contrast to his immense accomplishments, which really stand as some of the finest in organic chemistry.
A truly profound and heartbreaking story highlights the personal sacrifices and dangers that sometimes accompanied early scientific exploration. Now let's celebrate a pioneer who truly scaled up the possibilities of synthesis, particularly important for medicine. Percy Julian, 1899 to 1975.
Julian's work centered on the chemistry of steroids. These are incredibly complicated ring-containing molecules. They form the backbone of vital biomolecules like cholesterol and critical sex hormones such as testosterone and estrogen. His genius lay in figuring out how to synthesize these complex organic molecules on a large enough scale to actually make treatments for hormone deficiencies possible, like synthesizing cortisone from soybeans to treat arthritis. He even founded a company specifically for the production of these steroids, bringing these life-changing medicines to a wider population.
That's a massive leap from lab-scale synthesis to industrial production. Quite the achievement. And he broke barriers in more ways than one, didn't he?
Absolutely. Beyond his scientific prowess, Julian holds immense historical significance. He was one of the first African Americans to be awarded a doctorate degree in chemistry. And in 1973, he became the first African American chemist admitted to the National Academy of Sciences. His story is one of incredible perseverance, battling both scientific complexity and societal barriers to achieve monumental breakthroughs that benefited millions.
Now we turn to a figure often considered by many to be the greatest of all organic chemists. Robert Burns Woodward, 1917 to 1979.
A strong case can certainly be made for that claim. Among his numerous accomplishments, Woodward's syntheses of astonishingly complex organic molecules stand out. We're talking about compounds like vitamin B12, which he synthesized in collaboration with Albert Eschenmoser, as well as strychnine and quinine. These feats are particularly magnificent when you consider they were performed at a time when spectroscopic techniques, well, the tools for structure determination, were just a shadow of what they are today.
It truly is mind-boggling. I mean, without the tech we take for granted, how did they even begin to tackle such complexity? Imagine trying to build an incredibly intricate Lego castle in the dark, without instructions and only feeling around to know where the next piece goes. That's kind of what Woodward was doing, wasn't it?
That's a perfect analogy. In fact, he wasn't just building, he was inventing the very light sources and instructions needed. By pioneering several of those techniques himself, making these complex syntheses even more monumental. But his genius wasn't just in the lab. Along with Roald Hoffmann, he solved the puzzle of why certain reactions, called pericyclic reactions, where bonds are broken and formed in a synchronized cyclic dance, occur in the precise way they do. They cracked this using arguments about orbital symmetry, which is essentially understanding how the electron's natural paths or shapes around atoms dictate how they can interact, like pieces of a puzzle only fitting together in specific orientations. He won the Nobel Prize in Chemistry in 1965 for his outstanding achievements in the art of organic synthesis.
Yeah.
And it's widely believed he would have undoubtedly won the prize again with Roald Hoffmann for the Woodward-Hoffmann rules had he not passed away 2 years earlier, as Nobel Prizes aren't awarded posthumously.
His legacy truly spans the practical and the theoretical, a rare combination. Okay, next we have a true polymath, but also a rather controversial figure, Linus Pauling, 1901 to 1994.
Pauling was a force of nature. He famously used the then new field of quantum mechanics to describe the fundamental nature of chemical bonds, how atoms come together to form molecules. His classic book, The Nature of the Chemical Bond, completely revolutionized our understanding of how chemistry works at a fundamental level. After his foundational theoretical work on bonding, Pauling then pioneered the field of chemical biology and was instrumental in elucidating the structures of proteins.
So he moved from the very abstract to the incredibly practical and biological. That's quite a range. What's fascinating about Pauling, though, is how his strong convictions seem to define not just his science, but his entire public life.
Exactly. His personality was quite unusual. He was a vocal advocate for taking massive daily doses of vitamin C, for instance, and he was so outspoken against various government policies, particularly nuclear testing, that he was actually denied visas to attend major international science conferences during the Cold War era. This raises an interesting what-if in scientific history. Some have suggested that if he had been able to attend a specific conference where Rosalind Franklin presented her X-ray structures of DNA, well, with his unparalleled understanding of helices from his protein work, he might have figured out the structure of DNA before Watson and Crick. What's absolutely unique about Pauling is that he is the only person to win 2 unshared Nobel Prizes, one in chemistry, for his insights into the nature of the chemical bond, and the other, remarkably, in peace, for his uncompromising stand against nuclear testing and proliferation. It really highlights how personal convictions can both drive and, well, complicate a scientific career.
What an incredible legacy across such diverse fields. An iconoclast in every sense. Now, let's shine a light on a pioneer of structural determination through crystallography. Dorothy Hodgkin, 1910 to 1994.
Dorothy Hodgkin made incredible strides in structure determination using a technique called X-ray crystallography, a method that essentially uses X-rays to photograph the atomic arrangement within a crystal, allowing scientists to map out a molecule's precise 3D shape. What makes her story even more inspiring is that she accomplished all of this despite suffering from severe health problems, including crippling arthritis that often confined her to a wheelchair.
So despite immense physical challenges, she was just relentlessly persistent in mapping out these invisible molecular worlds. That's truly an example of sheer willpower meeting intellectual brilliance.
Precisely. She was extraordinarily persistent and hardworking. Her dedication led to the successful determination of the structures for many critical molecules, including penicillin, one of the first antibiotics, and later the incredibly complex structure of vitamin B12. Her work was fundamental in understanding how these molecules function, which is critical for drug development and biochemical research. She was rightfully awarded the Nobel Prize in Chemistry in 1964 for her groundbreaking work.
And finally, bridging us directly to the modern era of chemistry, we have John Pople, 1925 to 2004.
Pople's contribution was truly transformative for how chemistry is done today. He made the use of computational techniques practical and accessible. Essentially, he took theoretical chemistry out of what might have been considered the ivory tower and put powerful tools into the hands of wet chemists, those who actually work in the lab. Before Pople, these theoretical calculations were largely only available to hardcore theoreticians with advanced degrees in mathematics and specialized computers.
So he democratized computational chemistry, made it a tool for everyone involved in chemistry.
Yes, exactly. He was the pioneer of the Gaussian computational program, which is user-friendly computer software designed to carry out these complex molecular calculations, predicting structures, reactivity, properties, all without needing to necessarily do the experiments first in a lab. For his development of these computational methods, he shared the Nobel Prize in Chemistry. His work fundamentally changed the pace and nature of chemical discovery, allowing chemists to test ideas virtually before even stepping into the lab.
So what does this incredible journey through these lives and discoveries mean for you? This deep dive really shows that science isn't just a collection of static facts or dry formulas. It's a dynamic, deeply human endeavor. It's shaped by individual brilliance, remarkable perseverance, fierce rivalries, and sometimes even a little drama or personal tragedy. It's a story of constant questioning and evolution.
And if we connect this to the bigger picture, it highlights that the foundational knowledge we often take for granted today was built brick by brick, often by individuals with extraordinary stories and insights, many of whom faced immense challenges, both scientific and personal. It encourages critical thinking about how scientific understanding evolves, reminding us that every principle in your textbook has a fascinating, often surprising backstory, just waiting to be uncovered. It also shows the importance of those fundamental concepts, like carbon's tetravalency or molecular handedness, as the critical building blocks upon which all these complex discoveries were made.
What an incredible journey through the lives and discoveries of these remarkable organic chemists. From unraveling the fundamental nature of carbon bonds to synthesizing complex biological molecules and paving the way for computational chemistry, their contributions truly shaped the world as we know it.
And it raises an important question, doesn't it? Knowing these backstories, how does it change your perspective on the scientific principles you might encounter in a textbook? How many other unsung heroes or surprising anecdotes lie hidden in the history of science, just waiting for their deep dive? And what new insights might they reveal about the very nature of discovery itself?
Thank you for joining us on this deep dive into the human stories behind organic chemistry. We hope you found as much inspiration and surprise as we did, and that these individual journeys add a new dimension to your understanding of this incredible field.